Hi, good morning, good afternoon, and I'm very happy to be here. And today in this session, we will show you how to get the best performance possible in HANA with the HEX, its execution engine. So after a short brief introduction, we will talk a little bit about calculation engine. Then Manuel will take us deep into the internals of the HEX engine. We'll see how it works. And then finally, Elisabeth will give us very useful techniques and tools that will help troubleshoot any performance problem or unexpected behaviors that you might encounter. But first, why we do this session about HEX. HEX is our execution engine for all relational queries in HANA. It stands for HANA Execution Engine, simply. It replaced all the legacy engine that we used to have in older HANA versions, and we wrote it from scratch. So we took really the best techniques and technology, state-of-the-art features that are known in execution engines, and we used it to build HEX, and that's why we had much better performance comparing with legacy engines. But we will start first by the calculation engine. So why? Because that's part of one of the legacy engines, actually, but it's still existing, but it role shifted a little bit in order to delegate the execution to HEX, and we'll see how it works. So what's the calculation engine? So basically, it's the only component in HANA that's able to execute calculation views. As you all might know already, calculation views are graphically modeled queries that you can model using our modeling tool, such as BAS. It looks like this. This is a simple query as an example. And in BAS, there's like a myriad of operators that you can use to drag and drop and really graphically with the mouse model your query. We also have a bunch of operators that are only internal, that are not exposed in BAS, that we use internally for our internal stakeholders. And yeah, it offers a lot of advantages because you don't need to write any SQL to create very complex queries. And you can use a divide and conquer strategy in terms that you can divide the problem in smaller calc views and reuse these calc views to create even bigger calculation views. If you're interested, because we will not cover the modeling, but if you're interested, there's a session in the other track at 3:30, I think, given by my colleague Jan Zwickel, and it's dedicated on the calculation views modeling. But what we will focus in this session is the execution. And here is an example of a simple query, but if you see the join clause there, it's joining a calculation view with a table. And we'll see what happens when this query reaches HANA. So at first it's parsed. It's parsed by the SQL parser, and it will create, when it's not, of course, syntactically correct, a plan, the first plan that's not optimized. That's really a representation of the query. And you can see in the map here, the node here, it's the calculation view that is used in the plan. So far, we just know that we have a calculation view, but how to execute it. And now that we have HEX, we don't want the calculation engine to execute it. We want to replace this calc view with operation that HEX can execute. And this is what we call internally the unfolding. So the query optimizer, when it sees this calculation view, it will ask the calculation engine to unfold this calculation view, meaning the calculation engine will generate a equivalent subtree using only relational operation that HEX can execute, and we return them back. So it will be incorporated in the big plan, and we will have a big plan that containing only relational operation. All of them can be executed by HEX. So that's what we call the unfolding. And from step 4 onwards, the calculation engine is out of the picture. Its work is done. So that's why it's not responsible of the execution. It's more a compiler/optimizer. So because the plan will be executed by HEX in step 6 and to return the result. And this is what Manuel will talk about in details in the next part. But before we move there, I would like to tell you that sometimes the calculation engine fails to unfold a calculation view, and that has implications on the execution workflow and on the performance, and that's what we will see now. So back to the same example, and now here, back to the unfolding request that reached the calculation engine. Let's suppose that for some reason it fails. So first of all, the user does not get an error. The execution will continue. Actually, it's transparent to the user, but there's implication on the workflow. So what are these implications? So we cannot replace this node with its equivalent. It will stay as is, as a black box, as a calculation view that neither the calculation query optimizer nor HEX can execute. And all the way to the execution, it will stay as a black box that only the calculation engine can execute. And this is what happened. We end up with such a hybrid plan where part of it is excluded from the HEX pipeline and the execution plan and will be delegated to the calculation engine. And this is what happens actually during the execution. The calculation engine is invoked to execute this small part, and it will do its workflow of instantiation, optimization, generation of a plan, execution, and generation of the intermediate result representing this part. This intermediate result will be given back in the form of what we call an internal table or ITAB, and the execution can carry on to perform the join, for example, here. This is not ideal. This is not what you should have. This is not the normal. This is not a default behavior. Why? Because it's suboptimal. First of all, the query optimizer does not have a full view of the query because a big chunk of it is like a black box. It cannot optimize further. We have a hybrid execution plan. Part of it is totally excluded from HEX. And we have this ITAB in between, which consume a lot of memory. So we'll talk a little bit about supportability. So because like I said, you don't see it visibly that the unfolding was failed because you just get the result, but maybe slower. If you want to dig deeper and know what happened in the calc engine, one way is to trigger the tracers. We have many tracers that you can use. Each one is dedicated to a particular part of the workflow, but in case you don't know, I recommend to just use them all. And then you get a full trace describing the workflow that the calc engine did. And there are two ways to, at least the one I used to use. So either you create what we call a debug trace profile, which you can give filtering settings, like for example, to exclude users or restrict to a particular user. And then you give a name of a file, and then the list of all the tracer and their level. And here it's very good because you get one file, separate file from the main tracing file, and it doesn't have any noise because, for example, you can restrict to your user, and you can control what tracers to include. And you get it. You can get it, for example, in Business Database Explorer. Yes. And another way is to add to use the variable CE support this is another way to get a file per query. So it's very useful. It's very easy, actually. You have this select query, for example, that that I'm showing here, and you just add the last part in blue, which is the syntax that we use to provide values to variables, and the value of this should follow this particular syntax. So the syntax is easy. So it's a letter, which denotes the debug level, underscore the tracer. And then when you run it, you get the file. This, by the way, this only works for Calc Engine. It's not a feature that is supported by all components. So in the end, the file will contain all the detailed workflow of the calculation engine, containing the instantiation, the optimization, and the execution. And what I wanted to show you, if the unfolding is successful, you can see it in the traces. You can see the plan here, the project group by and everything that Calc Engine created and returned back to Query Optimizer. And you can see that it's written that it was successfully unfolded. That's the normal behavior. So if you have doubt on the performance, check the traces, check the unfolding to see that was successful. Yeah, so that's what we've seen so far. So how to generate the traces, how to read them, how to check the unfolding, and the impact of the failing unfolding on the execution. And with this, I will give the floor to Manuel, who will take us now into the internal of HEX and how HEX executes the query and returns the result. To you, Manuel.
Thank you, Mohamed. So, hello everyone. First of all, I'm Manuel. And in the next chapter of our journey, we will see and explore a little bit more in detail how SQL queries and unfolded calculation views are turned into an executable HEX plan. And my primary goal for this session is that you get a rough understanding, also the time given, we get a rough understanding of how HEX works internally. And I believe this will give you a good understanding of the capabilities, first of all, but also of the limitations of the execution engine that we currently have. Let me quickly walk you through the agenda. So I will give you a little bit of a motivation why we created HEX in the first place. Then we pay a little bit of a visit room into a little bit of a visit into the engine room of HEX to understand more the fundamentals and the internals of it. And I will conclude with recommendations, but I will keep it very short because Elisabeth is digging a lot deeper in there. So why HEX? Why was HEX a strategical necessity to be built in the first place? And to understand that, we have to have a look back to the time before HEX was introduced. And back then, we had to deal with a plethora of execution engines within HANA. So we basically had an execution engine for each persistence model. And even worse, for the column store, for example, we had in total 3 execution engines. There was the join engine, which was focusing on n-way joins, so it was highly optimized for that and was based on the concept of semi-join reduction. Then there was the OLAP engine. The OLAP engine was focused on star schemas rather, right? With a MapReduce-like processing model as the underpinning. And then we had, because the other engines had quite a lot of overhead, for OLTP queries, for simple ones, we had the single table search, which was trying to reduce the overhead of the other 2 engines. For row store, second persistence model, we also had another engine, right? ESX. And all of those engines were basically able to communicate with each other via so-called internal tables. Mohamed already mentioned that. Needless to say, there was a lot of maintenance overhead. So for each engine, you basically had your own experts. And those engines also had some technical limitations. So for example, for the legacy engines, they all used the so-called materialization model, where you had to materialize the entire intermediate result between relation boundaries. And also, of course, for the optimizer, it was very, very difficult to establish a global optimization between those heterogeneous engines. So this was a real technical limitation there. And with HEX, we wanted to get rid of it. First of all, of course, a primary goal for HEX is to replace the old engines, right? This was one of the incentive. And Mohamed already said it, so we started from scratch. And when you start from scratch, you want a state-of-the-art execution engine. And therefore, we focused on 4 technical architectural tenets, I would call them. So we use pipelining, which is known to reduce the memory consumption, in contrast to the materialization model. We produce continuous data flow, so to say, to improve the cache behavior and reduce the memory bandwidth. And what we try to do is we want to keep data as close as possible to the processor core, where data can actually be processed, meaning preferably in cache. But we try to push the envelope even further. And this is what code generation allows us to do. So we use code generation as well there. So we are cheating stuff in principle, but we don't brute force it on everything, but just use it where it makes sense. Like, for example, expression evaluation. And we will a little bit later on see how we use it. Then we use result streaming. So we produce continuous data flow. And as soon as tuples are ready to be handed over to the client, we will do that. So we don't have to produce the entire result. And finally, we use data-driven parallelism. And we use a parallelism that basically is steered by the data and by the volume of the data. Right? And later on, we will see how we do that in HEX. What we also wanted to have with HEX is, of course, to be extensible and modular. And extension essentially means that we are adding operators to the HEX engine. And what we also don't have, and this is something important because it distinguishes us from the legacy engines, we don't have any monolithic design assumptions. So like, for example, in the join engine, which was based on this concept of semi-join reduction, we don't know, we use it in HEX, but we build generic mechanisms. And this leads to a fully composable engines where you can piece parts the puzzle pieces like Lego bricks, so to say, right? As a result, we also have a very natural integration with the optimizer, and the optimizer actually has a huge responsibility to give us the most optimal plan. And we will, in the following presentation, we will see how that works. Now, HEX really in a nutshell. So the journey through HEX or to an executable plan. So we start at the client with a very simple SQL query, like the one here where you see a join on 2 tables R and S on an ID, and it has an additional predicate S-val greater than 10, which is followed again by a projection which extracts the relevant data for us. So RID and S state. And of course, the client wants to send this query to the database, where it sends it over from the SQL layer to the SQL frontend. Whereas first of all, it's parsed and turned into a canonical plan. As you might realize, this plan is highly unoptimized, right? It has 2 table scans, followed by a cross product, followed by a filter, which essentially contains the join predicate. And as a conjunction, it also contains the predicates S-val greater than 10. And this again is followed again by a projection, RID and S state, which extracts the relevant data. Now, the third step in optimization, and Mohamed already hinted at that, is rule-based optimization. And in rule-based optimization, you basically traverse the plan, and then you try to apply certain rules. For example, like in this case, you might try to replace the cross product followed by the filter, which is essentially a join, to turn it actually into an actual join, like in this case here. And this paves way for another optimization, in this case, predicate pushdown, where we get the predicate S-val bigger than 10 and push it further towards the table scan. Whereas first of all, it's efficiently or more efficiently evaluated. And secondly, it further reduces the intermediate results of the subsequent plan, which is very, very important in query processing. Now, the next step in this endeavor is the cost-based optimization. And you might have realized that we're only talking about logical operations like joins, but not about concrete algorithms. And the target of cost-based optimizations is to actually replace the logical operations by actual algorithms, like a hash join, for example, which now has a concrete built-in probe site. This is actually something that is heavily specialized for HEX already, because HEX provides a cost model. And the cost model is basically the performance profile of each individual physical operator that HEX provides. So it's heavily steered by that, and also heavily steered by cardinality estimations. Right, this is the input actually of the plan selection phase. Now here you might see another peculiarity, this pre-filter here. And this is some optimization that HEX has for the column store. So it has special predicate evaluation strategies for the column store. In contrast to that, we also have post filters, which are a simple evaluation-driven strategy, which on our side is entirely code-generated. The last step is to turn the plan into HEX. And we unfortunately have time to go into detail for the plan generation because it's a little bit complex, I would say. But this is essentially then the result. And the result is this executable plan here. Now, what is an executable plan? And you can imagine an executable plan as a number of pipelines where every pipeline is a continuous flow of data from a source operator to a sink operator. There is one concept that you still have to learn here, the concept of a pipeline breaker. So there are points in the plan where we have to generate the entire intermediate result. In this case, for example, we have the hash join. And before we can start the probe phase, we have to generate the entire hash table so that the plan makes sense. This would incur a pipeline breaker. Right? Another variant of a pipeline breaker you might imagine as a sort, right, where you can establish a global sort order only after you have seen the entire result. This also incurs a pipeline breaker. Now, how is the execution flow? And I hope the animation works. So the execution flow is basically, the first one is the vertical flow, and then we have the horizontal flow, and then we have the vertical data flow. So we start with the first pipeline, and the source operator in this case is the table scan R. And the table scan R pushes a chunk or some tuples to the next operator, which has the only task to insert it into the hash table. We might produce another chunk, right? Same story. We produce it and push it further to the build operator, which includes it again into the hash table. Now let's assume this pipeline is finished. We go to the next pipeline and start the process from scratch. The table scan operator produces a chunk, pushes it to the next operator, which in this case is a probe operator, which now has the task to look inside the hash table and try to find a matching partner. If it doesn't find one, processing stops. A new chunk is produced, pushed again. Let's assume in this case it finds a partner. He's lucky. Pushes again to the project operator and extracts the relevant data and pushes it further to the client. Now, this is essentially how HEX works internally. This is the data flow. Now you might ask, those pushing around of chunks and data and materializing them, isn't that expensive? And yes, you are right. And that's also one of the reasons why we use code generation, because code generation allows us to avoid this pushing of data and this materialization of data between the operators. So what we try to do with code generation is to fuse several operators together. So the resulting cogent operator contains the runtime semantics of all fused operators at once. But this is not the only thing that code generation gives us. I mentioned it already. It gives us also reduced interpretation overhead, because otherwise, say, for example, you want to evaluate an expression, either you need an interpreter, which is quite costly and has a lot of overhead, or you directly generate a machine code, which we do in this case. It also gives us the ability to inline and specialize. So during plan generation, we already know a lot of information about the plan, and we don't need to generate a generic code path, but can specialize it because we know the data types, for example. If strings are used, we only produce data, we only produce algorithms for the strings, nothing else. Right? There's no switches internally anymore. And then what I also mentioned in the beginning, we try to improve the cache locality. So we try to keep data as close as possible to the processor, right? Most preferably in registers. And this is something that code generation gives us as well. Now something very important, and this is the last tenet, it's parallelization. So what the legacy engines did basically is they employed a intra-operator parallelization strategy. So each operator had its own parallelization strategy, right? And we try to do that differently in HEX. So in HEX, we don't have it on a per operator basis, but across an entire pipeline. And to do that, we use two ingredients. One is a sampler, right? We try to measure the time of every job and try to find out how big a task size must be in order to be efficiently evaluated. And secondly, we have a task scheduler, which maintains a task queue on a per NUMA node basis, right? And in the background, we use a facility that basically knows the entire workload of HANA. So we start whatever jobs are necessary to process efficiently while keeping a balanced workload between other queries, for example. I keep it short, I promise. Recommendations. So I wanted to take some time to talk about cardinalities here, because cardinalities, they steer a lot of things on our side. You saw that the optimizer is basically makes decision based on those cardinalities because of the cost model that has been provided by HEX. And cardinalities influence algorithm placement. So for example, if you have the decision between an index join and a hash join, costs are the determining factor there. Join order as well. Most often you want, or always you want to have the most selective join in the very beginning to reduce the intermediate results for the subsequent plan. Cardinalities play a big influence there. Also, we have the ability to use reparallelization points throughout the plan. This is also something that is very much steered by cardinalities. So you want to have a look at cardinalities in the end when you try to assess whether a plan is sufficient or not. And what you should use if you're looking, for example, of the planvis graph here, on the right side, you should always use this hint here. And I just told you about code generation and its ability to fuse together operators. And the capability of HEX is also that it can fuse operators together across relations. And this impedes looking at the cardinalities. You don't see the actual cardinalities that are flowing from one relation to another. And this no fuse HEX cheat code, no HEX fuse cheat code hint allows you to separate those operators, those fused operators again, and you can see the actual tuples that went through from one relation to another relation. And this is very important. Here on your right side, you see the actual cardinalities that are flowing through the plan. And in parentheses, you see the estimated cardinalities. And if those don't match at all, the plan might be suboptimal, right? So there, of course, I have to mention cardinality estimation is not an exact science, right? The more joints you have in the plan, the wronger the cardinality estimation in the end. But if it happens right in the beginning, you might have some possibilities to join the plan shape a little bit to your preference. And this is something that Elisabeth will tell you how to do it. Also something that we stumble quite often over is regressions with memory. And for this, we in the meanwhile used a hint, which is called HEX memory statistic, which can be applied to a SQL query, beginning with QRC1. And this allows you to basically see accurate estimations or accurate estimations of how much memory an operator is using. And you can even drill further down into, for example, here the table scan and see those things on a per operator basis. And before QRC1, we had this telemetry allocator mode, which has a little bit implications on performance, of course, because it has there's a lot of tracing underneath. But this would have been a possibility that you could use also before QRC1. And with that, I hand it over to Elisabeth.
Thank you, Manuel. Thank you. All right, we only have 10 minutes left, so let's look at some troubleshooting. We'll use some familiar tools, and in order to look at some HEX-specific troubleshooting, we're going to use an example select query on top of a calculation view. And since we want to use HEX, the first thing to check is whether or not HEX is used. And this is incredibly easy. We can see it directly in the explain plan. If we see that the column execution engine has HEX all the way down to the lowest table scan, then we know that we have a full execution in HEX. This is not always the case, and one of the easiest things to check is whether or not our calculation view is unfolded, because we can see it directly in the explain plan. If we see that the HEX engine is partially used and the last operator is a calculation view, then we have a calculation view unfolding issue. As well, if we use the legacy engine entirely and we see column view as the last operator, then we also know that the calculation view is not unfolded. We also, in the column table name, can see directly which calculation view is causing the unfolding blocker. So if it's not unfolded, then we can use the CE support trace, which was just presented by Mohamed. And what we want to look for is the keyword node is QO compliant. And then we get an explanation for why this calculation view could not be unfolded. In this case, we have used an unsupported function, which is the above-lower function. We can find the same information in the planvis. You just have to drill down a bit further and look for those CE or calculation engine nodes. Then you also can find the QO blocker there. When we found the unfolding blocker, then we can try to remove it. Not necessarily always possible, but in this case, we can replace our above-lower function with the function lower. If we then run the CE support trace again, we can look for the keyword successfully unfolded. It could be that this already improves the execution and we have an execution in HEX, then we can end the analysis here. Otherwise, we can go back and check again. However, that's the quickest and easiest thing to check, but we can also have non-calculation view related HEX blockers. And a great way to find them is using the tracer QO HEX enum failure. Once you've taken the trace, you look in the trace file for the keyword QO HEX enum fail. There's a bit of a character length limitation there. And then you also get a rather good description of what is blocking the usage of HEX. I have two examples here. The first one is because I was running a query on a temporary table that is currently not supported in HEX. And the other one, the SQL optimizer estimated that a hard-coded limit from HEX would be met, and then it immediately defaults to the legacy engines. In the monitoring view, MSQL plan cache, you also have the column HEX rejection reason that you can check. And again, if you open the planvis in the SQL analyzer, you have this section called why not HEX. Well, maybe we could remove it, maybe not. Let's assume that now we have HEX fully used as the execution engine. Then we want to ask, or a typical question is whether performance is an issue. Performance is a bit relative. It really depends on the complexity of the query and whether or not you're executing a new query or an existing query has all of a sudden gotten a performance degradation. In case performance is not the issue, it could be the issue that we see a high memory consumption. Manuel has already shared how to analyze that issue. And another issue that we could encounter would be that we have some wrong results. If we don't, then we can end it here. If we do, then we can again go into the SQL analyzer. And if we have a new query, we'll have to look at the logic to see where the unexpected amount is being forwarded. And if we have an existing query and we are really lucky, maybe we have upgraded one system and see wrong results, and we still have a productive system on a non-upgraded version, then we can directly compare. And in this case, when we compared the two planvis files, we could see that the Windows node was sending 71 records where we were expecting 1. So some logic had changed or a bug was introduced. Depending on what the analysis shows, you can further drill down with several tracers. I don't have time to go through all of these, but you can see the flow of query execution here and which tracers would give you information about which step of the query execution. When we are talking about wrong results, especially for an existing query, it's also possible it could be a bug. So we suggest opening a ticket to SAP and including the following. information. And as a final note for wrong results, you can also try to execute the query with the hint no use hex plan. If it then gives you the correct result, then it's most likely a bug. However, that is not very usual to have wrong results. So it's much more likely that you have a performance issue. And a very easy first check is to apply the hint no use hex plan and see if it improves. If it does, there are some known performance killers. We talked about one already, partial unfolding or unfolded calculation views. We also know that for loops and SQL script procedures are a known performance killer, as well as skewed data. This is not necessarily only the case for the HEX engine. This could also be an issue for the legacy engines, but if you apply the hint no use hex plan and performance improves, then it could be for one of these reasons. You have a couple of options then. One is to accept to use the hint no use hex plan, and since we introduce improvements for the HEX engine with every revision of SAP HANA Cloud, you can then check with each upgrade whether the hint is still needed. Applying a hint is always considered a workaround, so we would hope to optimize HEX over time so that the hint would no longer be needed. If using the hint is not acceptable, then you can open a ticket to SAP. If you have bad performance and it doesn't improve when you add the hint no use hex plan, then or even gets worse when you add the hint no use hex plan, then we have to find the hotspot. In this, Manuel already shared how we can look for those in the planvis. And I just want to note as well that it's important when you're looking at the planvis in the SQL analyzer that you ensure that you're looking at the CPU time for HANA. This is, I believe, the current default. If this is not set, then you can set it in settings. It's important because if you don't set the CPU time, then you can't really trust this dominant plan operator. And this is a great tool to simply jump to the most expensive node to see where the time is spent. Manuel also mentioned the HEX no fuse JIT code hint, and this is really nearly a mandatory when you're taking a planvis file for HEX because, as Manuel already explained, as you can see in the side-by-side comparison, we have no card analyses, and all of the time has been fused into this upper node. When we use the hint, we get to see that the time that each step has spent. So in this case, we can see that index join is a little bit expensive. Another great way to see the time breakdown from the optimizer is to trace the SQL uptime. And then you see where is the SQL optimizer spending most of the time. And it gives you this great overview. And you can then further drill down into that substep to see the substeps of, in this case, the rewriting rule. And then finally, you can influence the decisions that the optimizer makes by adding hints, and based on the explain plan and based on what we saw in the SQL analyzer, we can try to find the right candidates for hints to be applied. In this example, we saw that the index join was a bit expensive, so we can try to add the hint no hex index join. You can find all the names of the hints in the hints table, and you can add them either directly to a SQL statement, you can add them as a statement hint, or you can add them inside of the calculation view. Just bear in mind that if you have an unfolded calculation view, you need to use the query level SQL hints. And if the calculation view is not unfolded, then you need to add them as Q or pop hints and execute in the SQL engine. With that, I hope there was something that you could take away from it, and the slides will be made available later. Thank you for listening.
That was an impressive amount of detail. So thanks a lot, Elisabeth, Manuel, and Mohamed for that. And I can see that we have first questions already. I guess it was you, right?
Yeah, I have maybe a question or maybe a request. I just Googled what you mentioned, the hint, no hex fuse JIT code. And assume how many results I get in Google. I get one. And my request is that we have better documentation about this, what you explained us, because the HEX is performing good, but there are cases where it's really bad, and we want to optimize it with some hints. And this is maybe not a question, but maybe a request. Yes,
I will take this with me.
Very fair feedback.
Thank you.
Absolutely. Over there. I'm not throwing, I'm running. So that's too far away and that would likely hit somebody. So there we go.
First, thanks a lot for the very insightful presentation. I enjoyed that a lot. The question is, do I have to take care of keeping my statistics current, or is it something HANA does underneath automatically?
The statistics, you mean memory or CPU?
Data distribution.
Data distribution is coming. It's not done by HEX itself, but it's done by a component of the optimizer, cardinality estimation.
Okay.
But they track samples basically, so they have several ways to go about it. But it's not done directly by HEX, but it's something that is influenced a lot the plant shape in the end.
It means we don't have to take care of kind of keeping that current. This is done by the
Exactly. We as HEX we are basically only the execution, putting together the optimal plan. So basically, this is influenced highly by cardinalities and done by the optimizer rather than HEX itself. Yeah.
Hey, there's one more coming down. There you go.
Thank you. Very detailed talk. Thank you so much. Just curious, if you're putting the hints on, is there any way to manage that down the track in case it's no longer needed, or way to check that, or you've just got to?
Due to time limitations, it was not so easy to cover all the
I
tips.
think you can go back, Elisabeth.
My screen. Okay. Yes, you can check in the statement hints system table all statement hints that are applied in the system. You can also add a comment to a statement hint so that you know why you added it, and then you can remove it again. And for the calculation view hints, we have a table. Let me just get the right MCE calc scenario hints, it's called. And there you can then see all the applied calculation view hints in the system. So that will give you an overview of what exists in the system, and then you can reevaluate whether you need them or not.
So on each upgrade, you can just run those again, check.
Yeah,
Yep.
That would be our recommendation, because any hint is a workaround. So
yes.
Yeah, it will not be removed automatically, so you
Yes,
have to do that yourself.
like that.
And like the problem is solved, then you remove the hint and go back to the normal default setup.
Thank you.
All right. Any more questions? All right, there's one. This time I'm definitely not. That's fine, but over there it was like, all right, let's see. Oh, that was decent.
Thank you a lot for a lot of details in this session. It was really insightful. Earlier today, there was a session somehow called You Think You're Optimizing for HANA. HANA doesn't think so. Yeah. Not sure if you were in there. Did you talk to the speaker? Could you clear it up? And
I think
second
Manuel
question.
can, yeah.
So just for a reminder for Manuel, because it was not in the session, the speaker showed a very simple example where he changed a predicate and the query optimizer, depending on the predicate, switched from HEX or not. And the same thing, the predicate was sometimes for equal 1 was HEX, for equal 2 was not HEX. So that was the.
I can explain it easily. Yes. So basically, the situation. First of all, I would have to know whether it's an on-premise system or whether it's cloud. On cloud, HEX is basically the de facto engine, so limits don't play a role there. But during development, to replace the other engines, we used limits, right? Where we knew that HEX wouldn't perform that well at that point in time. And sometimes, if the optimizer basically, for example, another predicate is introduced or the plant changes slightly, it might exceed this limit and it goes back to the legacy engine, or vice versa, go back or go to the HEX engine first, right? Because those limits are not exceeded. So this would be an explanation of such a situation that we saw there.
Yeah, okay, thank you.
Yeah.
That's
No problem.
cool. We could clear it up then. Yeah.
All right. In the interest of time, I want to say thank you so much for your session. I want to invite you to our expert corner, as well as everyone who has further questions. So they can meet you upstairs, the three of you, for a couple of more questions that you probably have. What I want to recommend is staying here for the next talk as well, especially if HEX and statement optimization is a topic for you, because Kuto will continue in 5 minutes from now on the topic of HANA statement hints. So maybe a quite related topic that you also want to join. So thanks again. Fantastic talk.